Okay, good afternoon. Many thanks for your time. So the agenda that I would propose is the following. We will start with the objective for the project, then review the abstract routing model, a few use cases, and then conclude and have the Q&A. So the objective for segment routing. On one side, it's to tackle issues reported by operators for years. For example, IGP-based fast route for any topology, or a simpler to operate, more scalable explicit routing capability. On the other side is to enable new SDN-based services. And the contribution here is to provide a more responsive and scalable interaction between the one orchestration, the applications, and the network. What we want to propose is an evolution. There's no revolution, so it means it must be simple to operate and especially very simple to deploy in the network, so support incremental smooth deployment. And I think it is the case. You'll see it through this presentation. The objective specifically for this NANOG talk is to be informative, to trigger your interest to read the draft. There's a wealth of details in the upcoming draft. I'll give the reference. They'll be published in 10 days from now. They are ready. Some of you already have access to them for review. Seek your involvement. And so today, on purpose, I'm brief. I'm trying to get your interest. We could speak a full day on it. There are many use cases. It will come later. The details are in these 5 drafts that, again, are ready and will be published in 10 days from now. I'll explain more on this later on. It's a real project. We have excellent endorsements and leadership from the service provider enterprise community. We've been working at least on a weekly basis with a large group of operators defining this technology in full transparency for more than 6 months. You can see some of the contributors to this technology on the right side on the first draft that we published in March. It's the result of multi-vendor consensus and positive collaboration. You can see that in the draft that we have now published from March, we have the constructive collaboration of Alcatel and Ericsson, so it's a multi-vendor, multi-operator consensus. Since March, we have received a lot of comments, questions, constructive feedback, some additional use case from Juniper. The reason why we have not published the draft yet is that we want to review with them first to offer them the ability to take part to this, join the work with us, and if they do, well, then we will submit all together the updated draft. So this draft will contain the architecture for segment routing, a long document on all the use cases reported by the operators, ISIS and OSPF extension that are very straightforward, PSEP extension for the SDN use case, and the fast route draft for the use case that I mentioned. On the side of Cisco, the EFT code is available since February on 12K, 9K, CRS1, and CRS3. We keep adding functionality to it, so if you're interested, don't hesitate to ask for the image, physical or virtual. And obviously, we're working on the productization. Don't hesitate to ping me also on this. So on the right side of the slide, you see those who really contributed to the technology definition. I'm based in Brussels, so running that project for Velocity. I took people in Europe in the beginning to have the Velocity. For the first draft publication in March, since then, we broadened the review and involvement significantly. There's much endorsement and implication in US, Japan, and China. This will be reflected in the new versions of the draft you will see published soon. So really trigger your interest to read this and contribute. We want this to be a multi-vendor constructive process, so we welcome any feedback review on this one. The abstract routing model. So segment routing. What is a 32-bit segment? A 32-bit segment can represent any instruction. It can be a service. It can be a context. It can be an IGP-based forwarding construct, and we're going to especially focus on this today. It can be a locator. An ordered list of segments express an ordered chain of topological and service instruction. That's basically your source route. Segment routing is based on the source routing principle. In segment routing, the ingress edge router captures a flow and push on the packets of that flow a list of segments that express the topological and service journey of the packet through the network. So the per flow state is only at the egress of the segment routing domain. Once the packet has been prepended with the list of segments, the rest of the network will simply execute the list of instructions where each segment expresses a specific instruction. A type of segment that is extremely key in the architecture are the IGP-based segments. We have two types of segments, prefix segment or adjacency segment, depending whether these segments are attached to a prefix information in the linked state database or to an adjacency information. A prefix segment steers the traffic along the ECMP-aware shortest path to the related IGP prefix. It's a global segment within the segment routing IGP domain. We also use the term a node segment. A node segment is a prefix segment attached to a prefix that identifies a specific node. It's, if you wish, a refinement of the term. An adjacency segment steers the traffic onto a specific adjacency or a set of adjacencies published by a node. It's a local segment related to that node. We call the segment routing global block the subspace of the segment space for the global segments. All the global segments are taken from that sRGB. And the operator manages that resource exactly like it managed an IP address block. It ensures that the global segments are allocated to unique prefixes. Let us review these two key segments, the IGP prefix segment and the IGP adjacency segment. Z, in this drawing, advertise a global prefix segment 65 with its loopback address Z/32. This is simple ISIS OSPF sub-TLV extension. All the remote nodes, therefore, installed the prefix segment 65 in their segment routing data plane along the shortest path to the related prefix Z/32. This is defined for IPv4 prefixes and IPv6 prefixes, and the details of the TLV extension are in these two drafts. The result is that if a packet is injected anywhere in the segment routing domain with a segment that is 65, that packet will be forced through the shortest path to Z, more specifically to the prefix Z/32 announced by node Z. So here you have the illustration of the packet path for a packet injected at A. An IGP adjacency segment. If C allocates a local segment 9003 for its adjacency CO, C advertises that adjacency segment together with its adjacency in the IGP, so it's a straightforward sub-TLV extension for ISIS and OSPF. C will be the only node to install the related adjacency segment in its segment routing data plane. That entry in its forwarding table forces him to steer the traffic onto the data link CO when he receives a packet with the active segment 9003. This is again defined for IPv4 or IPv6 adjacencies, and in these two drafts. So a packet injected at node C with the active segment 9003 is forced through the data link CO. Using these basic segments, one can build any path through the network. For example, if I want to build ABC OPZ, I can construct it as the list of segments 72, 9003, 65. Why? Because 72 is the node segment to C, and indeed, the first leg of my journey, ABC, is in fact represented by the node segment 72 from A. Once I get to C, the next leg of my journey, the next segment of my journey, is indeed represented by the adjacency segment 9003. And once I get to O, indeed the node segment 65 will get me to the node Z. And indeed, I can represent that path as the list of segments first do 72. Once you get to the node segment 72, enable the 9003, then enable 65, and it encodes your path. You can also express it as 72, 78, 65, where 78 is the node segment 2O, because indeed in this topology, the node segment 2O from C is also on the data link CO. So it's another way to represent the path. Very often, we will prefer to use node segments because they are multi-op in nature and they naturally support the ECMP awareness along the shortest path, which is very important for IP-based packet forwarding. And obviously, you can combine topological segments with service segments. So for example, if I want to build that strange path for a very specific reason because I want to have a firewall service at O, which is represented by O by the local service segment 9450, I can send the packet with that list of segments. The per flow state is only at A. A receives the flow, classify it, append the list of segments. The rest of the network is oblivious of the per flow state. It simply processes the segments one by one. ABC will forward along 72. When it gets to C, it will process the next segment. O will process the service segment associated to 9450. And then the node segment 65 will get it to Z. The segment routing control plane is extremely simple. It's lightweight extension to ISIS OSPF to distribute segments together with prefix or adjacency. It's applicable to IPv4 and IPv6. It is agnostic to the data plane. We distribute segments. It will be applicable to any data plane that can support these segments. And we're going to show how to do it in MPLS and for pure IPv6. For MPLS data plane, it's immediate application. We reuse the data plane as it exists. Why? Because the 20 rightmost bit of the segments are encoded as a label. And a list of segments is encoded by the entry point into the segment routing domain as a stack of labels. And when we complete a segment, we pop the segment. Once we are on the way of a multi-op segment towards a node segment, we simply swap the packets, the incoming label, for its same value. We keep the global segment on top of the stack until we reach its destination. If we reach the destination, we pop it, as I said, and we push at the entry. So we basically use the MPLS data plane untouched, and so there's a direct applicability of segment routing on the MPLS data plane. Applicable for the transport of IPv4 or IPv6 or other packet-based technology over MPLS. No change in the operation of the MPLS data plane, especially the segment routing control plane. These very simple ISIS OSPF extensions can live alongside the existing MPLS control plane. It coexists, it can interwork with LDP RSVP. It's also not needed to have LDP RSVP, but it can coexist, it can interwork with it. All of this is described in very details in the proposed draft. IPv6 data plane without any MPLS data plane. Well, first, all the control plane is applicable as is, because the control plane is defined for abstract segments that are data plane agnostic. So the only thing that we need to define for the IPv6 data plane support is how to encode a list of segments in the IPv6 data plane in a secure way. And that's basically, we're going to use a tunneling technique. We're going at the entry of the network, push another IPv6 header, and we apply to that outer IPv6 header a new type of routing extension header to secure it. So the high-level description of this was provided at the March IPv6 conference. We're working on the detailed draft in close collaboration with Comcast and other service provider and enterprise operators and academia. Any contribution is welcome. Again, this is being done in a constructive multi-vendor, multi-operator academia mode, and so we encourage any involvement if you are interested. Next section, the use case. This draft has 30 pages of use case. For revision 0, you can see it's very detailed, and there will be much more use case over time because every operator we have talked to see a use case for them. That's basically the experience I've seen. So there are many, many use cases. In this presentation, I will just show you the tip of the iceberg, some of the examples we have. First one, automated and guaranteed fast reroute. Directed LFA fast reroute is guaranteed in any symmetric topology. This is a result that we proved in 2002 when we were working on fast reroute, on IP fast reroute within Cisco. This was documented at the IETF many, many years ago in that draft. So that's very well known. The computation for it, it's very simple. It requires no extra computation over remote LFA, which is what is now supported by multiple vendors. And it is very easy to express because the repair stack is expressed as two segments, a node segment to the so-called P node, followed by an adjacency segment to the so-called Q node in the DLFA algorithm. So this technology to provide IGP-based fast reroute that is guaranteed to work in any symmetric topology known for 11 years is now made possible by segment routing. And so obviously, that's one of the flagship use cases, and a lot of operators in the process are interested to deploy this. Other use case. For example, many operators build a network with dual plane, a red plane, a blue plane, and they attach the edge devices to both planes. Let's say that Z, an edge device here, is connected to the two plane and advertise with its loopback the node segment 65. It is obvious that A here on the left, if it sends packets with the top segment 65, these packets will be load balanced across the two planes and across any ECMP path in these planes. Why? Because the node segment to a prefix follow the shortest path ECMP aware to that prefix. And in a dual plane design, the edge routers will load balance between the two planes and load balance across the ECMP path within the two planes. This is great for 98% of the traffic, 99 or more of the traffic. Sometimes service providers have specific requests to support disjoint-based services, a bank, a government. They buy two services and they ask them to be transported over disjoint path over the network. This can be supported very easily with segment routing. Let me explain why. First, remind a common design principle of dual plane networks. The gray links between the blue plane and the red plane typically are costed in the IGP with a bad metric, because once a packet is in the blue plane, it will reach its destination staying in the blue plane, same in the red plane. So let's assume this, it's a common design practice. So if we have this, it's very simple. You allocate an anycast IP address, for example, 1111/32, to all the blue routers. And to that IP address, anycast, you allocate a unique SID, prefix SID, let's say 111, from the global pool. And all these routers are provisioned with 111/32 and the prefix segment 111, and they advertise it in ISIS. So A now can send its traffic that needs the disjoint-based service with the list of segment 111/65. In MPLS, for example, with the label stack first 111, next label 65. The first segment is going to steer the traffic along the ECMP-aware shortest path to the first or closest instance of 1111/32, which in this case is the blue router number 1. Once it gets there, the first segment is processed, the next segment is processed, and 65, what it means? It's the ECMP-aware shortest path to 65. So it will be load balanced across the ECMP path in the blue plane. So now, with only per flow state at A can completely control the path of the traffic through the complete network. Most of the traffic is sent with 65. The traffic that needs to be restricted to the ECMP path within the blue plane are sent with two segments, 111/65. And the same could be done to restrict to the red plane. Another use case. Cost-based traffic, and these use cases are all real use cases of the operators that work on the definition of this technology. Again, this is a real use case, a worldwide single-level ISIS network with point of presence in Tokyo and in Brussels. Not Brussels, but another city in Europe for anonymity. That network has a lot of capacity over US, and so the shortest path in ISIS from Tokyo to Brussels is via US. That's great for most of the traffic, but the operator wants to enforce the voice over IP traffic from Tokyo to Brussels to go via Russia, where there's little capacity. Easy to realize with segment routing. you just ensure that the ISIS metric costs are such that the shortest path from Tokyo to Brussels is via US, the shortest path from Tokyo to Russia is via Russia, which is normal, and from Russia to Brussels is via Europe, which is normal. And then you simply allocate an Anycast address and seed to all the core Russian routers, and you can then traffic engineer your flow with only per flow state in Tokyo. Indeed, the edge router in Tokyo catch the data traffic to Brussels and send it with a single segment, the node segment to Brussels. This will make sure that this traffic goes via US and use any ECMP path along the shortest path, while the edge router in Tokyo catch the voice over IP packet that needs to go to Brussels and push on this package two segments. First, the Anycast segment to go to all the core Russian routers, and then the node segment to Brussels. The first segment is going to steer the traffic along the ECMP-aware shortest path to the first instance or the closest instance of the Russian Anycast address. Once the first segment is completed, the next segment becomes active, and the packet is then steered along the shortest path along the Brussels node segment, which from Russia we saw the shortest path is via Europe. And so this doesn't require any state per flow in the network. The only per flow state that you have is at the entry point where you capture your flow, you append your list of segments, and you source route your packet through the network. Another use case. This one was provided by colleagues at Juniper, and you can see a constructive collaboration process. We really wanted to incorporate all the comments, the clarification, the feedback, the use case in the draft that we will propose to them for constructive collaboration going forward. And so this was in some of the documents. It's basically how you can use segment routing to also control the engineering of traffic towards egress peers. So for example, here, AS1 is connected as a path to Z either via AS2 or AS3. And typically C here will have one single policy to prefer one AS or another. With segment routing, we can completely control the policy from the ingress router here A and B, and we can customize it on a per ingress border router basis. For example, A can send 80% of its traffic via AS2, while 20% of the traffic destined to Z goes via AS3. While at the same time, B decides to push all its traffic to Z via AS3. They are completely able to override the shortest path decision or the best path decision of the egress border router by using these segments that will control the decision of C for this egress-bound traffic. Another use case. That use case was in fact presented before the submission of the first public submission of segment routing by actually Google, colleagues at Google at the last NANOG meeting. That it's obvious that if you have these segments, a monitoring system in the network can source route the probes through a desired path to assess the viability of a specific path through the network. And that's exactly what they showed in February. So that's another applicability for segment routing. Then the final use case, SDN orchestration. But the last use case in this presentation, there are many more in the draft. The application requests, for example, 2 gig to go from A to Z with a certain level of SLA. The stateful PC element, part of the SDN orchestration device, is going to try to map this, and typically the best is to map it on the shortest path, which is the node segment to Z. But the stateful representation of the network will see that the node segment to Z, for example, is not viable because the bandwidth along the path here is not available. That link is full. So the stateful PC server will compute an alternate path. For example, it will find that this path has the necessary bandwidth available. So it will book the bandwidth in the stateful network representation, first step. Then it will translate the desired part into a list of segments, which is, for example, the node segments to C, followed by the node segment to O, followed by the node segment to Z. And then it will send a PSEP message to router A to say, build a per flow state where you classify this flow provided by the application, and on that flow you append the list of segments 66, 68, 65. And that's it. The only router that you need to provision, that the SDN orchestration engine needs to provision, is A. As soon as you have that per flow state at A will catch all the packets of the identified flow, append the list of segments. The rest of the network is completely oblivious of the nature of that flow. For the rest of the network, B and C, they just process the node segment to C. When it gets to C, C processes the next segment to O. And then when it gets to O, O, P, and Z will process the final segment to get to Z. The rest of the network has no per flow state for that flow. This is why we said initially that it's a building block of the SDN portfolio, because it allows for a model where the network is very simple. You don't need to go and control the network hop by hop. You do not need to signal hop by hop state on a per flow basis. It's very simple. It's only the ingress device that has a per flow state, highly programmable because you can steer the traffic however you want, and very responsive to change because the SDN orchestration device only needs to control the state of one device and not all the states along the path of the flow along the network. Conclusion, it's a very simple technology. Many people thought about it before, so the only objective we try to do is to deliver it on product and not talk about ideas or no. So it's very simple technology, lightweight ISIS OSPF extension, immediate applicability to MPLS data plane for IPv4 or IPv6 transport. For those who would like to not use MPLS data plane, we will propose a way to do it for IPv6 pure native. I explained it why before. Please, if you're interested, let us know, join the collaborative process. We have numerous use cases. There's significant confirmed industry interest. We committed to build the technology. We have committed deployment from operators already after 8 months of the life of that project. We have a very positive and collaborative multi-vendor process, so with Alcatel and Ericsson, where we're working constructively on defining this. We hope we're trying to do the best to welcome the collaboration with Juniper. We try to incorporate all the comments, the use case, the behaviors that they provided into the detailed draft. We will not submit them before the review because we would seek their involvement. And so it's really we seek a positive, constructive collaboration process. Your feedback and contribution is welcome. Again, we wrote very detailed draft to really support you to read this, get to use this, see whether there are use cases for you directly applicable, whether you have other use cases. Quite a lot of people came with the confirmation that, yes, they had this use case in their network. Others came with new use case. We really seek that collaboration. So many thanks for your time. I hope I initiated the interest to read this draft. And so we, again, welcome any contribution and involvement. Thank you.
Great, thanks a lot. Any questions?
I'll go first. Chris Luke, Comcast. So I was wondering how this does symmetric flows across the network. It's, all your diagrams shows the arrows going in one direction. Does it program it in both directions, and how is that distributed across the network?
What do you mean by asymmetric?
No, symmetric.
Asymmetric. But we have, it's a use case that we're going to document in the draft later on. We're working, there are 2 operators in the group that have this use case. For example, for very likely transport of a packet-based network where they want to retain this symmetric path where it's exactly the same path in both directions. There are multiple ways to build it. the way that we would propose, but again, it's a very transparent, collaborative process, so we have not finalized this, but the way we would propose to do it is that the SDN orchestration unit would instrument the two ends with that path.
Right.
That's the obvious way to do it in the mentality of the community at this time. This is where we have a huge investment, so I think it makes sense to do it like this. 10 years ago, we maybe would have built it with network-based signaling protocol. Maybe there will be people proposing this, so that's why I stay neutral. But what we are building us at this time is this, is do it on the basis of the SDN controller.
Great, thanks.
Thank you.
Okay, anybody else? All righty, thank you very much.